Today we're moving on from numerical solutions of ordinary differential equations to numerical analysis. That's a Fourier decomposition, a Fourier analysis. And that's going to be the topic over the next few classes. In today's class, I want to introduce the numerical methods, the numerical approach for Fourier analysis. So we'll talk about that. I want to introduce some of the issues and limitations of the numerical analysis, the Fourier analysis. And I want to look at some simple time series data in today's class. We'll look at other time series data in the next couple of classes. We've already created a lot of time series data from things like the rabbit population, which was time series data, to the damp-driven pendulum, which is also time series data. And we can apply this Fourier analysis, this Fourier technique, to all those types of data and lots of other data. This slide was just to illustrate what I mean by Fourier analysis or Fourier decomposition of some time series data. So in this slide upstairs, I've got you could imagine it to be an electrical signal, or you could imagine it to be a more abstract signal, but this electrical or abstract signal in black is a square wave. So you could imagine an electrical square wave as a function of time, or just some square wave function as a function of time. And Fourier analysis, Fourier decomposition is that you can build that square wave, you can kind of construct that square wave out of a sum of sine waves, a series of sine waves of different frequencies and different amplitudes. It's an interesting point because the square wave is a discontinuous function. The square wave just transitions from one level, say one voltage or one amplitude, to another voltage, another amplitude in a discontinuous way, whereas the sine waves, sine waves at different frequencies and different amplitudes, they're continuous functions. They're smooth functions. So we're able to build a discontinuous function out of a continuous function. So in this particular example, the square wave you can construct out of sine waves from this sort of simple sequence here. It's actually just a sum of all, look at the coefficients in the sine waves. It's all the odd harmonics of a particular frequency or a particular period of sine wave give you this square wave. To get the square wave, you've got to combine all those odd harmonics of the sine waves in a very specific way. The amplitudes of the sine wave are inversely proportional to the harmonic of the sine wave. So you look here, we've got a multiplier that's 1, 1/3, 1/5, and so on for all the odd harmonics. And that specific combination of sine waves will give you the square wave here. The red dash curve illustrated nearby the square wave is the sum of these first few terms in the sine wave series. So you see how out of the sine waves, even within a few terms, the square wave is starting to appear. Obviously, it's still smooth, it's not a square wave, but as we add more and more terms, we approximate better and better the square wave. Okay, so I'm going to, on this slide, just go through a few facts about Fourier analysis or Fourier decomposition or Fourier transformations. We use all those phrases kind of interchangeably. So a Fourier transform decomposes a function, let's say a function of time, into a distribution in frequencies. It could also be a Fourier transform could also decompose a function of space as the independent variable into a distribution of spatial frequencies. More generally, excuse me, the second bullet on this slide, that the Fourier transform transforms a function from a configuration space, and by that we would mean time or space, or some other configuration space, into a reciprocal space. So into frequency, as in time frequency, or spatial frequency, or some other reciprocal space. An important point, I have already mentioned it, is that Fourier, who obviously invented Fourier transforms, Fourier analysis, made this claim that you could combine continuous smooth functions to create a non-smooth discontinuous function. And so this whole idea was actually originally ridiculed as ridiculous. But we now know you can do this, and it is an extremely useful technique. So one of the features of Fourier analysis or Fourier transforms is that there's two distinct types of Fourier analysis, Fourier transforms. One is when you've got continuous smooth functions, so some analytical function, and you decompose it into continuous smooth sine waves, a series of continuous smooth sine waves. And another one is where you've got discrete data, a series of data points, and you decompose that data into a discrete series of sine and cosine waves with discrete frequencies. So there is the continuous Fourier transform or analysis, or a discrete Fourier transform analysis. And in our numerical work, we'll be focusing on the discrete data and the discrete analysis. If you were dealing with continuous smooth analytical functions, you'd be focusing on the continuous Fourier analysis. Typically, and mathematically convenient, we usually represent the Fourier transform is normally written in terms of not sines and cosines, but in terms of decomposing into this complex exponential. So terms with e to the I theta and harmonics of e to the I theta. So that's a complex quantity with an imaginary real part. But as you probably remember, you can break that apart. When you break the real part, it's just cosine theta, and the imaginary part is just sine theta. And it's just mathematically convenient to work with e to the I theta rather than cosine thetas, sine thetas. But still, the idea is the same, that you're going to break down some discrete function or continuous function into either a series of sine waves, cosine waves, or into these series of e to the I theta and its harmonics. The Fourier transform, Fourier analysis was, an interesting but not much used topic until the 1960s, when algorithms were developed for rapidly calculating Fourier transforms. And that opened up the possibility for Fourier transforms, Fourier analysis for analyzing data. Since then, Fourier analysis of time series data is a huge topic. It's a huge topic in physics and beyond physics. Okay, just a few more comments about its importance. When we hear sounds and language and music and interpret those sounds as language and music, there's a Fourier analysis that's going on in our brains, in our heads. Our ears are detecting the Fourier components of the sounds in the music or the language. And out of those Fourier components that the ears mechanically detect, we reconstruct in our brains. We analyze those series and reconstruct the language of the music or whatever itself. So Fourier transform is hardwired into our head. As I mentioned, it's a ubiquitous tool in mathematics and science and beyond. It's a incredibly commonly used tool in mathematics, science, and beyond. As I put one example, famous example here, you know, the discovery of DNA was a discovery of DNA based on a Fourier analysis of X-ray diffraction data. So that's a famous example of using Fourier analysis for a big breakthrough discovery. Another topic I mentioned there, just because we had just been working through ordinary differential equations, we talked about numerical ways of solving ordinary differential equations, but Fourier decomposition, Fourier analysis is another broad way of solving differential equations. Okay, so let's talk about the mathematics of the Fourier transform or the Fourier analysis. And I think I'm just reminding myself right now here, I'm going to focus on the discrete Fourier analysis rather than the continuous Fourier analysis, because that's what we're going to work on in our Fourier numerical solutions for Fourier analysis. So the forward discrete Fourier analysis would take you from data in the time domain, time series data, to the data, to the corresponding data in the frequency domain. So that would be a forward discrete Fourier analysis. The inverse Fourier analysis would be if you had data in the frequency domain, frequency series data, then that a inverse Fourier analysis would take you to the time domain. And so that there's forward and inverse analyses that take you from time domain to frequency domain, take you from frequency domain back to time domain. There's two equations for the forward Fourier transform and the inverse Fourier transform are these two equations here. So I better say what's in those equations, because we're going to be using these equations as we do our Fourier analyses. So the lowercase x and the uppercase x are arrays. They're the time series, they're the time series data and the frequency series data. So lowercase x is the time series data and uppercase x is the frequency series data. I labeled the time series data with lowercase x subscript n. N is the index of the time samples, and I've labeled the frequency data as uppercase X subscript K. K is the index of the frequencies and the frequency data. And so here is in curly brackets, right? I'm imagining some set of time series data in the time domain. It's a series of samples obtained at different times. X naught was the sample at time 0, x1 the sample at time like time tick one, x2 is the sample at the next time, at time tick 2, and so on, so far, up to the total number uppercase N of samples. So that's our time domain data. And this will be in curly brackets down here, uppercase X this is the frequency domain data. So X0 is the frequency data for the lowest frequency, x1, the next frequency, and to the next frequency, and so on. So this is just how we're going to label the data, which in essence are just arrays of numbers in the time domain and in the frequency domain, the upper and lowercase x's and lowercase n's and lowercase k's as the indices for the particular elements of the time series or frequency series. So if you look at the two equations, you can then see, once you recognize the lowercase x's and the uppercase x's, that the first equation is computing the frequency series data corresponding to some time series data. So on the right-hand side, we got lowercase xn, that's the data in the time domain, and we're converting it to the frequency domain. So that's the forward transform. And then downstairs here in the second equation, well, we see on the right-hand side, that's the frequency domain data. And we're determining from it the corresponding time domain data. So over here now on the left-hand side is the time domain data. So those are the two actions of the forward and inverse Fourier transforms. And the conversion involves weighting either the time domain data or the frequency domain data by this complex exponential here. And summing over all the data, summing over the time domain data in the upper equation, summing over the frequency domain data in the lower equation here. So that's how you compute the Fourier transform, say the frequency domain data from the time domain data by this weighting of the time domain data and summing over the time domain data. And similarly, almost identically for the frequency domain data. If you want to calculate the time domain data, you weight the frequency domain data by this complex exponential and you sum over all the elements of the frequency domain. So that's how you accomplish the transforms. Notice the two sums in the forward transform, you're summing over the elements of the time domain data. So n upstairs here is different for each element in that sum. In the lower equation, you're summing over the elements of the frequency domain data, that's the k, and so k is changing the weighting as you sum over all the elements of the frequency domain data. I'm just checking that I said everything I wanted to say about those two equations, and I'm realizing I didn't say everything I wanted to say. If you started with the time domain data, you use the upper equation to convert it to the frequency domain data. And then you took the frequency domain data and converted it back with the second equation to the time domain data. You should get back where you started. The fact that there's no 1 over n in front of this summation, but there is a 1/n in front of this summation, is one way of achieving that requirement, right? That you get back to where you started if you do the forward and then inverse Fourier transform. And this is a typical way of normalizing the time and frequency domain data with this 1/n here, so that you get back your requirement that if you do the direct and the forward and the inverse transform, you get back to where you started. Sometimes you'll see a normalization where it's actually a 1/√n in the lower equation and a 1/√n in the upper equation. But you could imagine that will get you back to where you started as well. So there's a choice of normalization that was going on here. The other thing I wanted to say was a little bit about, well, what's the weighting by a complex number that's this exponential term. What's that weighting doing? What that weighting does is it basically, the weighting picks out when it goes from time domain to frequency domain, it actually picks out the different frequencies so that you can build the frequency spectrum. And that weighting, when you go from time domain to frequency domain, picks out the different time samples when you go from frequency domain to time domain. So it's the particular weighting that does the job of picking out the frequencies that are in the time domain data, or picking out the times that are in the frequency domain data. And that's exactly the weighting that you need. I mean, I'm not deriving it. I'm just saying it, that's what that weighting's purpose is. Okay. So this slide discusses how we might implement this calculation, because we want to implement calculating the frequency domain data from some time domain data in Python and NumPy. How we might implement it in a Python code using a NumPy library. So a very, very convenient way of implementing this calculation on the left is using Python and NumPy vectors and matrices and its linear algebra. Because we can then write the Fourier transform, which we, on the last slide, we wrote it in this form over here on the left, and write it as in this simple way over here on the right, as the product of a matrix times the time domain data to give the frequency domain data. So this is very handy to implement in Python with NumPy. The way to think of it in terms of this matrix vector linear algebra is that our time domain data is like a vector or an array with time samples in it. Our frequency data is like an array or a vector with our frequency domain samples in it. So those are two vectors. The lowercase x and the uppercase x are two vectors or two one-dimensional arrays in NumPy. The multiplication and then the summation can be written as multiplying, if you're going in the forward direction, the time domain data with this matrix, or if you're going in the inverse direction, multiplying the frequency domain data with a similar matrix, where this matrix, the elements of this matrix, are all these e to the I pi k n values for different values of k and n. Okay, remember, n is counting which sample in the time domain you have. A is counting which sample in the frequency domain data you have. So N distinguishes the columns, K distinguishes the rows in this matrix. And look, these 2s and 4s and 8s and 16s and 32s, if we went deeper and deeper into this matrix, those are just products of K and N. So K is incrementing as you walk vertically downwards. N is incrementing as you walk left to right. Upstairs in this top corner, we've got K and N being 0. Then we've got K here, K and N being 1. We've got K and N being 2. We'll get a 2 times 2. And so that's how this matrix is constructed. It's really all the values of that e to the I pi kn divided by the number of samples that we wrote down here. So if we can build this vector and this matrix in Python and NumPy, we can multiply the two together to calculate the time domain data. That's all we've got to do. We'll just do this calculation here. Or if we know the frequency domain data and we can build corresponding inverse matrix, then we can calculate the frequency, the time domain data by matrix product. And that's what we plan to do. Okay. Losing all my titles here. Just a few technical details about this calculation that we're about to do. So we're planning on a pretty simple calculation in the context of Python and NumPy, where we're just going to build a vector, build a matrix, and multiply them together and calculate the frequency domain data or calculate the time domain data, the data that we don't know. So that's the plan. And these are just some technical details about what we're going to see as we do that. The first point is that our time domain data, we're going to imagine those as just real numbers. So it's as if we've measured some quantity, real quantity, physical quantity as a function of time. So they're just going to be a series of real numbers. So they might be, the location of the moon in the sky or something like that, a set of real numbers, or the voltage or the current in the circuit, a set of real numbers as a function of time. The frequency domain data will be complex numbers. If you think about the calculation, we're taking real time domain numbers, multiplying them by a complex quantity. So we're going to get complex numbers. So the frequency domain data will actually be complex numbers. Interesting thing about the frequency domain data. So imagine this array that is the frequency domain data. The first half of that array, the second half of that array, so the top end and the bottom end, are mirrors of one another. They're mirror images of one another. They're like basically copies of one another. So the frequency domain data has, in some sense, sort of the frequency domain mirrored in two halves about the center of the frequency domain data array. So we'll see that. So that's what I try to indicate here. There's a copy of the frequency domain data that is in the first half of the matrix. The array. The array has uppercase N elements in total. So the first half of it, up to n over 2, is one copy of the frequency domain data, and the upper half of it from n over 2 and above is the second copy of the frequency domain data. So that's a special thing about the frequency domain. It has these mirrors. Well, you might imagine this is kind of, I was sort of hoping that everything would be nice and symmetric. We started talking as if everything was nice and symmetric when you went from the time domain to the frequency domain, or you went from the frequency domain to the time domain. The equations look kind of symmetric, looked rather symmetric. But now I've just broken the symmetry of the time domain and the frequency domain data in two different ways. One of them was, I said, that the time domain data is real numbers, the frequency domain data is complex numbers. And the other way was that the time domain data is just one copy of a series of time samples, but in the frequency domain, we got these two mirrors of the frequency domain data. Although we have broken that symmetry, although in that sense the two data sets are organized rather differently, there's the same amount of discrete information in both data sets. So in the real data, the time domain, we've got n, uppercase N, real numbers. In the time domain data, in the frequency domain data, we've got n over 2, n divided by 2 complex numbers. But that's the same amount of discrete data. So n real numbers and n over 2 complex numbers, because the complex numbers have a real and imaginary part, it's the same total amount of information that's stored in those two time and frequency arrays. So they do store the same amount of data. Okay. Let me say something about, in this bullet here, about the frequency range. So we measure some time domain, some time data. What's the range of frequencies for the frequency domain data? Well, the range of frequencies is determined by the sampling rate that you sample the data at, your time domain data. And the range of frequencies that you see in the frequency domain go from 0 frequency, so that's the lowest frequency, that's the lowest frequency bin in the frequency domain, up to half the sampling rate. That's the highest frequency you see in the frequency domain. And that half the sampling rate is called the Nyquist limit. So that's when you sample data with a certain frequency. Maybe I sample data at 1 hertz. Every second, I measure the current of the voltage in a circuit. So that's a period of 1 hertz for my measurements. So my sampling, a period of 1 second for my measurements. My sampling rate is 1 hertz. The highest frequency that I can see in my extract from my time domain data is going to be half that. It's going to be not 1 hertz, the sampling rate, but it's going to be half a hertz. That's the highest frequency I see. So that's the point here, that the range of the frequencies is from 0 to the Nyquist limit, which is 1/2 of the sampling rate. So if I was sampling at 1 hertz, my frequency range is 0 to half a hertz. What about the step size in the frequencies? Like the frequencies, like the time domain data, are discrete data, and measure the time domain data every second. So with a frequency of 1 hertz. What is the interval between the discrete frequencies in my frequency domain data? Well, the interval between the frequencies in your frequency domain data is just your sampling rate. So that's the S subscript S divided by n, the number of samples in your time domain. So that's the step size, the interval between individual frequencies in your frequency domain. So for example, just to make it more concrete, supposing again, I sampled my data once every second. I'm sampling my currents or voltages once every second, so with a frequency of 1 Hertz. Supposing I collect 8 samples of that data, I make 8 measurements, each separated by 1 second. I collect a 1 Hertz data rate. Then in the frequency domain, the frequencies in my frequency spectrum, my discrete frequency spectrum, will be the interval between them will be the 1 Hertz, the sampling rate, divided by 8, the number of samples that I took. So the frequency domain with 8 samples would have spacings between measured frequencies that are 1/8 of a Hertz. So you can see there that obviously if you want a finer spacing in the frequency domain, you need to collect more than 8 data points. You would want to, if you collected 80 data points, you'd have a 10 times finer frequency spectrum. If you collected 800 data points, you'd have 100 times finer frequency spectrum. So the number of data points you collect will determine the granularity, the coarseness or fineness of your frequency spectrum. One other point. We said that if you, the range of frequencies that you collect in your data, the range of frequencies of your frequency distribution that you extract from your data is from 0, the lowest frequency, up to the Nyquist limit, half the sampling rate. So that's the range. What would happen? What would happen if you had a frequency in the data that is higher than the Nyquist limit, higher than half the sampling rate? Do you just not see it? Yeah.
Well, it doesn't have periodic.
Yeah, so that's a very important. You're right that it's not that you just don't see it, right? If it's higher than the Nyquist limit, it's higher than the sampling rate, you do see it and it is distorted. So your answer is exactly right. The quantifying that a little bit, its frequency gets what we call aliased, or kind of folded from being higher than the Nyquist limit to actually being lower than the Nyquist limit. So if you have a frequency in your data that is higher than the Nyquist limit, higher than half the sampling rate, it's not that it vanishes from your frequency spectrum. It will appear at a lower frequency in your frequency spectrum, and it appears at this frequency. So FA is the alias frequency, this folded frequency, this lower frequency that it appears at, and it's just the frequency that is the difference between the sampling rate and the frequency that is higher than half the sampling rate. So to give an example of that, suppose I was sampling at 1 Hertz, my Nyquist limit is half a Hertz, my signal is 0.6 Hertz. It's above the Nyquist limit. I can't see 0.6 Hertz. Where do I see it? I see it at the sampling rate 1 Hertz minus the frequency of the signal, 0.6 Hertz, which is 0.4 Hertz. I see it below the Nyquist limit, an aliased frequency, at a folded frequency. And so that's a feature. We said that in the frequency domain, the frequency domain samples are complex numbers. They have a real part and the imaginary part. The real part tells you the amplitude of that frequency in your data, how large or small that particular frequency contributes to your data. The imaginary part actually tells you about the phase of that frequency in the data. I mean, the phase could be different. The crests or the troughs of the sine wave could be a different location. So the phase, the imaginary part of the complex number tells you about the phase. There's information about the phase. Okay. I got a couple of slides here to kind of reinforce some of the information I said there about the time domain, frequency domain vectors, and then a little bit about the matrix multiplication to accomplish the forward or the inverse transform. So this slide here asks us to imagine that our time domain data was 8 samples. So we just made 8 time measurements. And it then asks us to imagine what the frequency domain data looks like. There'll be 8 samples in the frequency domain. Let me stress though that nobody in their right mind would ever collect 8 samples worth of time domain data and do the Fourier transform to the frequency domain data. Normally you're collecting hundreds, thousands, millions of samples of time domain data and doing a Fourier transform to the frequency domain data. So collecting such a small number of samples is completely ridiculous, except if you want to kind of look at the some of the patterns or relations between the time domain data and the frequency domain data in these vectors, lowercase x and uppercase x. Okay, so if I imagine let's imagine I've collected 8 samples with a sampling rate of 1 Hertz. So I've got a sequence of 8 samples, 1 second between each of them, so the duration of total 8 seconds with sampling rate of 1 Hertz. What are some things I can infer from that? Well, the maximum frequency, the Nyquist limit for my frequency distribution is half the sampling rate, so it's going to be half the Hertz. So I'll only see frequencies up to half the Hertz. That's the highest frequency I can see in my frequency domain. The coarseness or fineness of the spacing between discrete points in my frequency domain was going to be the sampling rate divided by the number of samples. That's 8 samples divided by it's 1 Hertz divided by 8 samples, so it's 1/8 Hertz. So that's the spacing between the frequencies that I'm capable of measuring. And that's the point where to have a fine measure, this is a very coarse measurement of frequencies. So I wanted a fine measurement of frequencies, I have to have many more data points than 8 data points. Okay, the frequencies are themselves, I have enumerated them here, from 0, we said that was going to be the lowest frequency, up to half a Hertz, that's the Nyquist frequency, with a spacing of 1/8 of a Hertz, or 0.125 Hertz. So there are just these 5 frequencies. Those 5 frequencies are in the first 5 elements of the time domain, frequency domain array here. So the first 5 elements step from 0 Hertz to the Nyquist limit in this interval of 0.125 Hertz. So that's all the data is packed in there. These data points up here are the mirror of this. So this one here is also 0.375 Hertz. This one here is 0.25 Hertz. This one here is 0.125 Hertz. The 0 Hertz is not repeated in this mirror. So it's even more complicated, just the mirror. The mirror, the 0 Hertz is just one entry in the frequency domain data. And also the highest frequency is not repeated in the mirroring, in the frequency domain. This just sits in the center. And so when I say that there's a copy or there's a mirror of the frequency domain data in the top half and the bottom half of the frequency array, it is a copy except for the lowest frequency and the highest frequency, which only enter once. That's a big effect here. But if you had 1,000 samples or 10,000 samples or 1,000,000 samples, right, it's just one little data point at the extreme ends of the frequency spectrum. So this is what the arrays would look like. This is what the matrix looks like that you're going to multiply the time domain data by to get the frequency domain data. And it's also what the matrix looks like for going in the inverse direction, where you multiply the frequency domain data by the to get the time domain data. The matrices are the same, other than a minus sign in the exponent. So I plotted the matrix in four different ways here, or at least I plotted components or aspects of the matrix in four different ways. So remember that we've got a 8 elements of time domain data, and we've got equal size array for the frequency domain data. The matrix is then an 8 by 8 matrix that multiplies the time domain to get the frequency domain. So we need an 8 by 8 matrix. So whatever the dimensions of our data, supposing it's 1,000 or 1,000,000 data points in the time domain, it'd be 1,000 or 1,000,000 data points in the frequency domain. It'd be 1,000 times 1,000 or 1,000,000 times 1,000,000 array. You can see you can get big arrays with Fourier transforms, and that's why you need fast Fourier transform algorithms. Anyway, so this is 8 elements vertically here, so eight rows. 8 elements horizontally, so 8 columns. The columns are labeled with the index of the time domain n, and the rows are labeled with the index of the frequency domain k. So each element in the 2D matrix is a particular frequency and time domain label on it, a particular value of n and k. What I'm plotting is the values of that complex exponential. One important thing is here I'm plotting the magnitude of e to the I 2 pi lowercase n lowercase k over uppercase n, plotting the magnitude of it. It's 1 everywhere. E to the I theta always has a magnitude of 1, right? So that all these matrix elements have a size of 1. It's just their phases varying with the frequency index and with the time domain index. Here's how the phases vary. So this is the phase, the complex phase of this of these complex numbers that are the elements, and you see that phase is changing from 0 through to pi back towards 0. So that's the change in the phase that's occurring when think about the exponent again and the exponential. It's I 2 pi lowercase n lowercase k over uppercase n. So that the values of n and k are going to change the phase, and that's what's happening here. This is the real part and the imaginary part of the matrix, just to show that it has generally has real and imaginary parts. I don't have any words to describe it, but it's interesting just to see it. Okay, this side shows you then what happens when you take some time domain vector, say an 8 element vector, you multiply it by the matrix to get the frequency domain vector. Here's my matrix. I just shown you the real and the phase parts upstairs here, but that doesn't change that with the data. So that's independent of the data. It only just depends on the number of samples of the data, but it doesn't depend on the values of your time domain data. And it doesn't depend on the values of your frequency domain data. It's just depending on how many samples of data you've got. So you can construct the matrix that you're going to multiply without knowing what the data is. You construct the matrix just knowing the size of the data. Here's a sample of data. When we talked about the vector, we talked about collecting 8 data points. Say measurements of currents or voltages in a circuit, and here are 8 time domain data points. And these meant to correspond to a square voltage. So imagine the voltage was 1 volt, for 2 samples, dropped to -1 volt for 2 samples, up to 1 volt for 2 samples, down to -1 volt for sample for 2 samples. That's the time domain data. It's like a square wave. If I take that data and this should be a this is a typo here. This should be lowercase xn. If I multiply the matrix by the vector lowercase xn, I'm going to get the frequency domain data. That's what I've plotted over here. So this times this matrix gives these two panels here, where I'm showing you the real part and the imaginary part. What you discover is that in the amplitude of the signal in the frequency domain, you've got one bin where there's a non-zero amplitude, and it's at 1/4 hertz. So it's the bin that corresponds to 1/4 hertz. Remember, with these 8 samples taken at 1 hertz, our frequencies that we can see are 0 to 0.5 hertz, the Nyquist limit. We see a frequency at 1/4 hertz, which is the frequency of the signal, right? The period here is 4 seconds. It's 4 time interval, so it's 4 seconds. So that's a frequency of 1/4 hertz. So we'd expect to see a signal at 1/4 hertz in the data, and we see it here. And so that's an example of a simple Fourier transform. We just took 8 samples on a square wave, but we saw in the frequency domain data the frequency of the signal. I just wanted to show you one more, just to convince you. This is the same matrix. And I've collected 8 samples, but now the signal that I've sampled has a lower frequency, a longer period. The period now is not 4 samples, but the period here is 8 samples. So it's like a square wave, but I'm just seeing this one period of the square wave. So when I multiply this vector, which I've got to correct down here, by this matrix, I get the complex array of numbers that is the frequency domain data for it. And it tells me that this signal has a frequency component at, let's see, 1/8 of a hertz and 3/8 of a hertz. Well, look, the 1/8 of a hertz makes obvious sense, right? This is a square wave that has a period that is 8 samples, so 8 seconds, so a frequency that is 1/8 of a hertz. So obviously we expect to see 1/8 of a hertz. Well, there's also a 3/8 of a hertz. Where do the 3/8 of a hertz come from? Well, if you remember back to that very first plot I showed you as an example of Fourier transform, if you have a square wave, the square wave is made out of a series of odd harmonics. The lowest one has the frequency of the square wave, so it would be 1/8 hertz, but then there would be another one coming from the next odd harmonic, and that would be the 3/8 hertz. There would be a 5/8 hertz, but I'm not seeing it because it would get aliased to a lower frequency, and it actually gets buried in these guys here. So anyway, this is second example of Fourier transform. Okay, I want to go on to implementing it in the code and just show you some cases where it's not such a ridiculously small number of samples. They help us learn a little bit about the oddities of the frequency domain and the time domain, like the complex versus real numbers in those 2 different names, like the mirroring in the frequency domain, like the Nyquist limit in the frequency domain, other features of the frequency domain. But let's do some more practical things. I think I'm going to just switch to my code. Okay. So this is the first cell of my code, and it's just importing some functions that I'm going to use and defining a user function that's going to be my own Fourier transform function. So of course, here's the old friends, NumP and matplotlib, because we want to use arrays, vectors, matrices, and their multiplication. And we want to be able to plot the results. So those are familiar to us. Two new things here. I'm going to write my own function to accomplish the Fourier transform. It's going to be a very simple and straightforward function that I think is clear to read it. Yeah. Okay, so I'm going to write my own Fourier transform, and I think it's going to be nice and clear where I understand how it works in terms of this matrix multiplication. I'm also going to use a library package Fourier transform. I'm going to do that because my Fourier transform that's simple to read is slow, very slow. We try to take the Fourier transform of a large amount of time domain data. We'll be waiting to next week. So we'll use also a SciP package for the Fourier transform. I've somehow moved where I am in the code. So you see this third line here, I'm importing FFT from SciP, that's the Fourier transform. I also import inverse Fourier transform. I'm not going to use it here, but just to show you. I also import a helper function, I think of this, is to properly label the frequencies in the frequency domain. So it's just a little helper for us. This is my function, user function for accomplishing a Fourier transform. So the work I did was really in writing this function. What this function does is going to take an array of data or a vector of data from the time domain. So lowercase x is going to be the data in the time domain, and it's the argument of the function. And then it's going to return the corresponding data in the frequency domain. So in the language of the slides, it's going to return uppercase X with the K index. So argument is the time domain data, return is frequency domain data. So this simple as that. And here's the calculation. These 5 lines here. First thing we got to know if we want to do the Fourier transform is we need to know the size of our time domain and frequency domain data. We need to know the size because we want to construct a matrix. We were calling it M, that we're going to multiply our time domain data with to get our frequency domain data. So I want to know the size of the domain data. So that's this first step here. I'm getting the shape of the of X. This is just giving me the length of X. This could be length of X. So N is the size of the array in the time domain. It'll be the size of the array in the frequency domain. Next 2 lines. Next 2 lines, I'm defining lowercase n and lowercase k. They're going to be arrays or vectors. One's going to be a column vector and one's going to be a row vector, because they're going to help me build the matrix. So the array lowercase n is just an array of all the indices n that label the time domain data. So it's an array of size uppercase n that goes from 0 to uppercase n minus 1. It's just those labels of the time domain data. And the same thing for the array k. It's a one-dimensional array that is just going to label the frequency domain data starting from k equals 0 to k up to k, a k value of n minus 1. So those are the labels of the frequency and time domain data. This reshape thing here, I want one of them, because I'm going to build a matrix out of it. I want one of them to be a column vector, one of them to be a row vector. If one of them is a column vector and one of them is a row vector, I can multiply one by the other to make a matrix. So that's the key thing here. Supposing I had a row vector and then a matrix vector, sorry, a column vector, and I multiply them this way. But I go whack, I go one number. That's one number. If I multiply them this way around, there's a lot of multiplications that are going to go on here. There's going to be n by n multiplications that are go on as I multiply this out, and I'm going to get a n by n matrix. So this is dimensions n, this is dimensions n. One way of arranging the multiplication of the columns and the vectors, I just get a object of dimension 1 here. This is going to be n by n. So that's why one of these is column, one of these is row. When I multiply them, which is what I'm doing here inside this line, that's making a matrix. So that's one exploiting NumP here, right? Exploiting the NumP will handle things like vectors and matrices. It allows me to build a matrix out of two vectors, a column vector and a row vector, by simply writing their multiplication. So that's very handy here. So this is where the matrix gets built in this product here. And then this whole equation becomes a kind of matrix equation defining the matrix M. If you think about the exponent of the matrix M, it was minus I, so J is I, not P, for some reason, times 2 pi. So here's my 2 pi, times the products of K and N, the two labels, divided by the array size, the data set size. And so this line takes those two vectors, a row vector and a column vector with the indices K and N, constructs the whole matrix M for them in one shot. And it really is exploiting NumP and how NumP can handle, variables, vectors to matrices and so forth. Once I've got the matrix M, we said that to get the frequency domain data, uppercase X, I've just got to multiply together the matrix M and the time domain data, lowercase x. And I'm doing that with a NumP function. This is a dot, is a NumP function. The arguments are the two things that you want to multiply. Dot's very flexible. You can put in two vectors and do vector multiplication. You can put in matrices, do matrix multiplication. Here I'm putting in a vector and a matrix and doing that multiplication. So here's my N, the transformation matrix that takes you from one domain to the other. Here's my time domain data, the lowercase x. This is going to return my frequency domain data, the uppercase x, which is what I'm returning from the function. So I think this is, real NumPy Python was really convenient for expressing, for building a Fourier transform out of that matrix vector representation of a discrete Fourier transform. I would say that this little bit of code is simple and straightforward to do the Fourier transform, but it hides the fact that this little bit of code is very slow in doing the Fourier transform. The time taken for this code to do a Fourier transform is the dimension of your data, so uppercase N squared, because it has to work through every element of this matrix. And that's a very slow way to do a Fourier transform, and that's what the fast Fourier transform beats considerably as a more complicated algorithm for performing a Fourier transform. So FFT up here that we imported from SciP is a fast Fourier transform. So they should yield the same results, they just take different amounts of time. Okay. This is the code. This cell is in the code where is that a hand up or?
Well, yeah, I'm just wondering, so, the array that you get from that function would be an array of frequency values?
Yeah, it will be frequency sample, yeah.
It would be frequency values, related to that time. And then, but how do we define an amplitude?
Let me say what you were saying a little bit different. It's an array of amplitudes in frequency space that say, the amplitude is large, that's a big frequency component in your
That's a big
data.
contributor.
If the amplitude is small, there's a small component in your signal. If the amplitude is 0, there's no component of that frequency in your signal. So I might have frequencies that are 0, 0.125, 0.25 hertz. And the size of those numbers associated with those frequencies is how much those frequencies contribute to your data.
Okay. Okay, so. Well, so the x-axis is essentially the same because it's just which part is in.
The axis in the frequency domain is frequency. The axis in the time domain is time. But each one of them, at each of the frequency intervals or each of the time intervals, there's then the amplitude of the signal. And then in the time domain, it says how much of that, how much amplitude there is at that time.
Right.
And in the frequency domain, it says how much amplitude is there for that frequency. Okay. So I'm going to generate a few different periodic signals, and then I'm going to do a Fourier transform with my code, and we'll see if we can understand the Fourier transform of these periodic signals. I'm going to define a couple of quantities here. All of them, I'm going to take 1,000 samples. So NP is the number of data points, the number of samples I'm going to claim. T_0, that's the period of the data. I'm just going to take periodic data. I'm going to take sine waves and other periodic data, square waves. So that's the period. And this is the corresponding frequency. So let's imagine that this is a sampling at 1 hertz. There's 1,000 samples, so we sampled for 1,000 seconds. The period was 100 seconds, so the frequency is 0.01 hertz. Here is where I can define my proxy for a independent variable, time. So time goes from 0 to 1,000 seconds. And here in these 4 lines, I'm going to define different signals. The first one is just a sine wave, whose period is 100 seconds, or frequency is 0.01 hertz. And then I'm going to replace it with a square wave and a sawtooth, and I think we'll just stop there. Okay, so coming out of these first group of lines, we've got a function. We've got a time-dependent function that, for some reason, at this point, I've started calling y rather than x, but that's fine. Lowercase y is now my time-dependent function, and in this particular cell, it's being defined as just a sine wave. Sorry, highlight. This line, all that work I did on introducing the matrix multiplication for the Fourier transform and then writing a user function for it is used here. This is that function, discrete Fourier transform. The argument is the time domain data is going to return the frequency domain data. And as I say, for some reason I've changed to using y's, uppercase, lowercase x rather than x. Y is uppercase and lowercase rather than x is lowercase and uppercase. But this uppercase Y is frequency domain, this lowercase y is time domain. I'm slicing the data to remove, I'm remembering the fact that the data is mirrored in that array. And so I'm just keeping the bottom half, slicing off the top half. You know, when you've got 1,000 elements, samples, then you're keeping the bottom 500 and throwing away the top 500. The other thing I'm doing, this is where I'm using this helper function that I said is useful. This helper function provides labels for the frequency axis. It provides you with units for the frequency axis. So the way the helper function works is that you say how many data points you've got. Remember that determines the coarseness or the fineness of the frequency axis, so it needs to know that. And then it needs to know the interval between data points. Now, I sampled every second, so 1 second. So if I got 1,000 data points sampled at 1 second intervals, it's gonna return, this function returns an array of the frequencies in hertz that correspond to my frequency domain. So it's very handy. Obviously, you could do that yourself. It's handy to call this function. So having got through those 2 lines, I've done my Fourier transform, and then I'm going to plot 4 plots here, I think, which is the original data in the time domain and then the data in the frequency domain plotted in different ways. I'll just go on and show you the plots. Upstairs is the time domain data. So we said we've got 1,000 seconds, 0 to 1,000, a period of 100 seconds, periods 100 seconds. So we've got 10 cycles, so that makes sense. And the amplitude of the sine wave was 1, is unit amplitude. This is the, so I know you can't read the scale of it, but this is the magnitude of the frequency signal in the frequency domain. This frequency, this is signal in time domain. This is the signal in the frequency domain. The amplitude of the signal. I mean, by amplitude, I mean the frequency domain signal is a complex number. This is the size of the complex number. Oh, look at it. It's 0 everywhere. It's 0 everywhere except one location. This one location is 0.01. This frequency is this data is a single frequency at 0.01 hertz. So that's exactly what we expect. So we see a spike here because this is single frequency data. The amplitude of that is a little bit subtle. It depends on your normalization, how you do the normalization. I mentioned that 1/n versus 1 over the square root of n and another 1 over the square root of n. With the 1/n normalization, if you've got a single sine wave in the data that has unit amplitude, its size in the Fourier transform, the frequency domain, is the number of samples divided by 2. This is 500. It's the number of samples, 1,000 divided by 2, because it has a unit amplitude in the frequency domain. So that's how a unit amplitude frequency will appear in the, unit amplitude in the time domain will appear in the frequency domain. This is the, I can't even read it. That's great. The green plot is the real part, and the magenta plot is the imaginary part of that complex number. We see that there's a huge negative power here. In the real, this is has a zero real component. Its phase is this number here. So it has has its phase is such that it has an imaginary, it's just an imaginary number. But it's just related to the phase of the signal in the time domain. If I shifted the phase, I would shift where the balance between the real and the imaginary parts here. I just want to show you then the other two, or at least one of them. I'll show you one of them. The homework assignment is to perform a Fourier transform like this on some simple data. If I go to the square wave, because we talked about that at the beginning. Here's the square wave in the time domain, the same period, 100 seconds, same total range, 1,000 seconds. We said a square wave was built out of odd harmonics of sum of sine waves of odd harmonics. Here's the first one. Here's the next one, So this would be like the n equals 1, n equals 3, n equals 5 that I plotted on the very first slide of today's class, and 7 and 9 and so on and so forth. So this is, you're seeing here, the sine wave expansion Fourier series for a square wave. You're seeing how to build a discontinuous square wave out of a summation of sine waves, continuous functions. So this is the amplitude of their contributions. If you remember, the amplitude of the first term in the square wave was 4 over pi. Well, here it will appear as 4 over 5, which is just a bit bigger than 1, right? Times the number of samples divided by 2. So it's a number a bit bigger than 1 times 500, which is this 600 and a bit here. So this has the right amplitude for the lowest harmonic in a square wave. And the other ones decrease in that series of 1, 1/3, 1/5, 1/7, 1/9,